Hey you, it's me. Today we're going to go over a little more general of a topic that'll set us up for future leetCode problems. We're going to cover linked data structures. But before we dive into that, let me briefly mention arrays, which are not linked data structures. Arrays are these ordered structures that, by definition, have a fixed size and can only hold a single type of object. When we create arrays, we normally allocate a space in our memory that's large enough to hold X many objects. We can imagine the space allocated as a long row of slots that can hold different instances of the same type. To access any of these slots or instances, we need to know the starting position of our sequence. And from there, we can just count using an offset, which from now on we'll just refer to as the index. Before I dive into this example, I just want to make it clear that this is a really simplified version of how things work. In reality, there are different levels to memory. Some sit in the CPU, and others are external to it, like RAM. For simplicity, we'll pretend that everything we create today is in our RAM. For this example, let's allocate some space for an array. Let's make the array size 7. Now we can fill the slots up with objects. One drawback that we know about arrays is that if we need more space, we have to allocate a brand new series of slots, and then copy over the data from the old space, and finally deallocate that data from its original position. Thankfully, most of us get to enjoy modern arrays, which are data structures that act just like the arrays that we described, except they handle resizing automatically. One advantage that arrays do have is based on the principle of locality. Essentially, that principle states that we tend to access the same objects in memory over a short period of time. For example, in a for loop, we continuously access the counter or the array that we're iterating over. Because arrays are long continuous sequences, when the CPU has to read, for example, index 3 from memory, it's been optimized to read the values at index 3 minus k and index 3 plus k as well. This saves on further trips to the memory. All of that makes an array a memory access optimized structure, and it attributes to its great performance. Okay, so that was a really quick intro on arrays, but we need that so that we can compare arrays to linked lists and see where they fall. When you think about it, we've all used a linked data structure in one way or another. If you've used a map, hash table, or a queue in any modern language like Python, Java, Golang, then you've used a linked data structure. Linked data structures are just objects that hold references to another object.
What exactly do I mean by that?
Well, for the case of arrays, when we visit index X, we know where the next element is because arrays are sequential. Therefore, X plus 1 would be the next slot that we go to. In the case of linked data structures, we lose that sequential structure, and so objects are scattered all over the memory, and instead they hold pointers or references to each other. We'd normally store the reference to the next object in our linked data structure under some key called next, or a hash that was created from some unique ID that the object has. If we wanted to visit every object in a linked data structure, we'd have to read the first object from the memory, then get the memory address of the next object to visit under the next key. Then we'd read that new object and repeat, where we look at our next key, find the memory address, go to that memory address, find the next key. So how does the principle of locality work for us here? Well, it is true that we still tend to access the same memory over a short period of time. However, because we didn't allocate a space to place our objects into, as we create them, they get scattered all over our memory, and therefore we actually lose the hardware optimization to read nearby data. At this point, you might be asking yourself,
Why even use a linked data structure if it's going to be slower?
So glad you asked. Let me explain. There's no need to resize a linked data structure because the data isn't stored in sequences, so you don't have to reallocate anything when you run out of space. Sure, sequential data access might be slower, but we can store data in ways that actually reduces the time complexity when we execute something, like finding the minimum element in O log n versus n for the case of an unsorted array. Or like appending to the head of a linked list in O1 versus ON for the case of an array. Over the next couple videos, we'll introduce more complicated structures and talk about their advantages and disadvantages. But for today, let's start simple with a linked list. A linked list is a collection of objects. Each object points or references to the object that comes after it. So in array terminology, that would mean that object at index x only knows where object at index x plus 1 is. All we really have to do is keep a reference to the head of the list, which is the first object in our collection of objects. A more common term for objects is node. We call them nodes because each one of these objects holds together the larger structure. Let's implement a linked list and a few useful methods for managing it. First, let's define our node class. Our node class will have two properties: a value property, which holds whatever data we want to hold, and a next pointer, which holds information on where the next node is. Now that the building block for a linked list has been defined, let's write a linked list class, which holds a reference to the head, and implement methods to manage these nodes. I wanted to point out these two representation methods. These allow us to stringify our object so we can actually get the value from the linked list that we want, instead of just getting the hashed memory address. These are definitely something that you should implement. The first method we will implement is the length method. It's going to return the number of nodes that are in our list. The idea here is as follows. I start with my head pointer. If it's not none, I increment my counter. Then I check the next node. The one thing we have to pay attention to here is potential nulls or nones. If the linked list is empty, then the head can be none. We'll make this our base case and just return 0. Next, we'll hold a reference to our linked list head in this temporary variable. The reason why we can't use the head as the variable to iterate over the list is because we'll lose a reference to the start of the list if we change its value. So we'll set our current equal to our head, then keep iterating as long as current is not none. And for every iteration, while current is not none, we'll increment our counter by 1, and we'll reassign our current variable to be equal to current.next. This moves it one node down the chain. Then return the count once we're done iterating. So what's our time complexity? Well, we can treat every iteration as O1, and if the length of the list is size n, then we have O(n) time. And here, I just wanted to demonstrate two things. One, how we actually use our class that we just created for the linked list. We need to initialize a new instance of this class. Here, I've called it LL. And secondly, we can access the length method from our linked list. And when we run it, we can see here in the terminal that we have a list size 0 because we haven't put anything in the list yet. What's the use of a length method if you don't even have any nodes to count? Sounds like we should implement an insert method. First, let's discuss where an insert would place a new node. Traditionally, a linked list inserts a new node at the head of the list. So every new node replaces the old head as the new head, which is kind of the opposite of what we do with arrays. If we inserted 1, 2, 3 in that order into a linked list, we'd actually get a linked list that looks like this, 3, 2, 1. Okay, I think we're ready to start writing the insert method. We can start by taking a value parameter. This parameter will take whatever data we want to store in the new node. We always want to address our base case at the beginning of our method. And the base case for all of our linked list methods will rely on if the head is none. Now what we do in our base case will differ depending on the specific method, but in this case, if the head is none and we have nothing in our linked list already, we'll just go ahead and insert our new node as the head. And we don't have to specify what our next node would be because there's no other node in the list. And before we exit our base case, we'll just return. So in the case where head is not none, meaning we do have at least one node in our linked list, we're going to make sure that we set the existing head as our next pointer for our new node, just like what we saw in the example a few minutes ago. Notice that this new node is going to become the new head of our list because we're inserting it at the beginning, not at the end. That means our new node's next pointer should point to the current head of the list. And then we should update our head reference to be this new node. Okay, quick question. What's the time complexity here? Well, all we pretty much did here was create a new node and assign it some property. No loops, no recursion, so that gives us an O1 time. Here we can see our newly defined insert function in action. Taking my new instance of a linked list, I'm going to insert 1, then I'll insert 2, 3, and 4. If I print what the list looks like, we can see 4 is the head of our list, followed by 3, 2, 1, and 1 points to none. So we can see right here in front of our eyes that we just replaced the head every time we inserted a new node. But what if we actually wanted to insert a new node at the tail of the list? How would we do that? Well, let's take a look at what we learned from our length and insert methods and see if it can apply to this at all. First, we can copy over the base case from our insert method. If the list is empty, then inserting at the head or the tail is all the same. Next, if the list isn't empty, then we need to iterate over all the nodes to get to the end. Our length method did just that. However, we need to be aware when we're about to reach the end of the list. The reason why is because we want to assign our new node as the next property of the current last node in the list. Just like before, we'll define a temporary variable called current and assign it to the head of the linked list. We use this as a reference to the node that we are currently visiting when we iterate through our linked list. So how do we identify the last node in the list? This check will come up again and again inside a linked list. We'll update our while condition to check as long as current node is not none and current.next is not none. This condition will hold true for every node in the list except for the last one. Because, naturally, if it's the last node in the list, then its next pointer is none. Just like we did in the length method, we will move our current pointer to point to current.next in every iteration. And then once we exit this loop, all we have to do is initialize our new node and assign it to current.next. And once again, we have an O(n) time complexity just like we did with our length method. Here we can see I used the insert at tail method to insert 1, 2, and 3. We see the output down here, and it's the opposite of what we found when we did our regular insert, which inserts at the head of the list. Here, our node ordering reflects more of what you would see from an insert method on an array data structure. Now that we've covered ways to populate a linked list, let's see how we can find a specific node in the list. Every node has a value property, so that's what we'll be looking for. It's possible that multiple nodes have the same value, but we're just going to return the first one that we find. Before we start iterating through our linked list, let's create the current variable and start at the head of the list. Similar to length, we want to visit every single node in the list. Next, at every iteration, we just want to check if our given value matches the value of the current node. If it is, then we'll return that node. If not, we're just going to move our current node to be equal to current.next. If this value didn't exist in our linked list, we can just return none. Maybe you noticed that we didn't have a base case for this method. Because if head is none, our while condition would not be met, and therefore our while loop wouldn't run, and we would just by default return none. So for this method, we don't really need a base case. And for this find method, our time complexity will be O(n). Here you can see I gave us two examples. The first example I called our find method with the value of 2, because I know that 2 is in our list. For the second example, I tried it on a value that I knew was not in our list, and we can see down here. Because of the representation methods that we defined earlier, we see here that we actually print out our node with the value of 2 and all of the consequential references it has down the line in its linked list. Under it, we can see we print out none because 5 is not a value in our linked list. The final method that we'll cover today is called pop. Pop is the opposite of an insert. It removes the head of the list and replaces it with the head's next node. So before we remove anything, we should check if we even have a head node. That's our base case. If we don't have a head node, in this case, we'll just return none. Then we want to update the head property of the list with the next property of the head. However, to avoid losing any reference to our current head, we should put it in a temporary variable. So once we've stored head in a temporary variable, then assign head.next to the head property. After that, we can return the old head, which is in our temp variable, just like this. A cool thing about this pop method is that the time complexity will be O1, since we're removing the head of the list, which we have that predefined reference to. This is fantastic in comparison to something like an array, which would cost us ON to do this type of removal. And in this final example, we can see down here, I call the pop method on our populated linked list, and it actually returns 0, because in this example, I had inserted 0 at the head of my list. And subsequently, it's the head of the list that gets returned when you call a pop. And you can notice under where we printed out 0 in the terminal is the new list without 0 as the head node. So we just built our very own linked data structure. Always try to visualize how the current pointer advancement is, as that's normally where things get a little tricky. Once you have that down, linked lists become fairly simple. Now, obviously, modern languages have pre-existing implementations that you should always prefer over your own implementation of a data structure, because there's no need to duplicate work that's already done. However, as you begin to implement more complex software, knowing the differences between the data structures that you use and how they operate under the hood is very important. Additionally, during interviews, you're more likely to have to implement these operations from scratch. Thank you so much for checking out this linked data structures video. As always, if there's any pattern, algorithm, or problem on LeetCode that you want to go over, let me know in the comments. Don't forget to like and subscribe, and from me to you, have a great day. Some sit in the CPU, and others are external, not eternal. Memory is forever. CPU is forever. Now that we've covered ways to populate